The example that we just studied matched the secular terms of the second order expansion so well because the initial conditions were chosen such that the particle in question stayed away from any resonant conditions, meaning that no significant resonances arose. However, in the case where resonances can exist, we must also consider resonant terms in order for our approach, the use of a finite order expansion of the disturbing function along with the linearized form of the Lagrange planetary equations to have predictive power. So let's consider a case where M2 and M3 are in a 2-to-1 resonance. If we are anywhere in the vicinity of a 2-to-1 resonance between M2 and M3, it will be the case that 2n3 is approximately n2. That is, twice the mean motion of body 3 is going to be approximately equal to the mean motion of body 2. This means that in our disturbing function expansion, we now need to consider all of the secular terms and any terms of the form 2 lambda 3 minus lambda 2, because these are the ones that are going to lead to canceling out, and these are going to lead to cosine behavior that is of greater period than the periods of the orbits, and lead to long-term changes in the various orbital elements. So let's see if any such terms exist in the direct part of the disturbing function. By inspection, we see that there are two possibilities for terms like this to arise. The first one occurs here, where in this cosine argument, we have j lambda 3 plus 1 minus j lambda 2 minus var pi 2. If j is set to 2, then this argument becomes 2 lambda 3 minus lambda 2. So we now need to add to our existing secular terms this term only for j equal to 2. The other place where we can get the proper combination of lambdas is in this cosine argument, where again, setting j equal to 2 will give us 2 lambda 3 minus lambda 2, in this case minus var pi 3. In all other instances, we either have both lambda 3 and lambda 2 being multiplied by the same j, or lambda 3 being multiplied by j and lambda 2 being multiplied by 2 minus j. And so that combination, that 2-to-1 combination, is not going to arise anywhere else except for these two terms and only for j equal to 2. We also need to check the indirect part. Remember that there were no secular terms in the indirect part. However, if we look at RE, because again, we are considering the perturbative effects of body 3 on body 2, here too, we will gain one new term. It is located here, and we clearly see that we have 2 lambda 3 minus lambda 2. This combination does not arise anywhere else in this expansion of the indirect part of the external perturber disturbing function. Just as we did for the secular perturbations, we catalog all of our new terms, giving their coefficients new names, C4 and C5, in addition to the C1, C2, and C3 that we had for the direct part of the secular perturbations. These two new terms define the resonant direct part of the disturbing function, and now we have a non-zero indirect part for the resonant perturbation of this form. And let's just quickly recall how we are going to package all of this together. All of this is going into this R2 disturbing function. We have mu3 over A3 times the direct part, which now contains a total of 5 terms. And we have mu3 over A3 times A2 over A3, the thing that we've been calling delta, times the single term out of the indirect part. We plug the average of that R2 expression into our linearized Lagrange planetary equations, and for the resonant terms only, we thus get this set of differential expressions. We predict a time rate of change in the semi-major axis of body 2 of this form, two sinusoidal terms with the same argument with slightly different coefficients. The time variation in the eccentricity of body 2 has a very similar form, the same sinusoidal variation times a slightly different amplitude, and the exact same thing for var pi 2, except 90 degrees out of phase, since this is cosine, this is sine. And we are predicting that due to the resonant perturbation, there is no variation in the longitude of the ascending node of body 2. It is crucial to remember that these differential expressions are operating at the same time as the secular ones. Just because we now have resonant perturbations doesn't mean that the secular perturbations go away. So let's quickly recall what our secular theory predicted. We predicted no variation in the semi-major axis, sinusoidal variation in the eccentricity, and linear variation in both var pi and capital omega, so strictly linear changes in the longitude of periapsis, and the longitude of the ascending node. These variations will be operating at the same time as our resonant variations. However, our approach will be to analytically integrate these in isolation and then just sum the two solutions and see what happens. Even in isolation, these are not straightforward to analytically integrate. We have to make a couple of more assumptions before we can find closed form solutions to these differential expressions. What we are going to assume is that the only time varying quantities in these expressions are the arguments of these cosines. That is, only the lambdas and the var pi's are going to be allowed to vary in time on the right-hand side, and we are going to ignore, again, on the right-hand side of these things, any variations in the semi-major axis, mean motion, and eccentricities. We are going to assume that those are quite small effects and just do the integration without considering them. For the variation var pi 2, we will use the secular prediction, that is strictly linear change in this one parameter, so that we can actually do this integration. Making all those assumptions and carrying out these integrations, we find that we get very similar forms for the solutions of each of these three expressions. And so just as an example, we can take a look at any one of them. We will look at the eccentricity expression. We carry out the integral of E2 dot, making all the assumptions we just listed, and we get something that looks like that is, the eccentricity of body 2 will be approximated by its initial value plus the mean motion of body 2 times the ratio of semi-major axes, A2 over A3, this delta term, times the ratio of the mass of body 3 to the mass of the central body M1, times that C4 coefficient from the direct part of the disturbing function, all over twice the mean motion of body 3 minus the mean motion of body 2 minus the time rate of change of the longitude of periapsis of body 2, and then all multiplied by these two cosine terms, one of which is just a function of the initial values of the mean longitude of body 2 and the argument of periapsis of body 2, and the other one being a function of twice lambda 3 minus lambda 2 minus var pi 2, which is exactly the form of the cosine arguments that we picked up from the direct and indirect parts of the disturbing function due to this resonant condition. So while this looks rather cumbersome, all this is telling us is that we expect sinusoidal variation with this argument of the eccentricity due to the resonant perturbation. As already stated, we will get exactly the same solution forms for each of these first three differential expressions, save that there will be two separate sinusoidal terms for the semi-major axis expression, but each of them will have exactly the same argument, meaning that we expect overall for there just to be one single periodicity and phase for the variation in semi-major axis. So our prediction is that the resonant perturbation causes sinusoidal variations in semi-major axis, eccentricity, and the longitude of periapsis. At the same time, we predict that the resonant perturbation produces no change in the longitude of the ascending node. We take these predictions, we add them to the predictions of the secular theory, and then we test the results. And that is done here in this example from Murray-Dermott. This example, just like the one that we considered for the secular perturbation case, is considering a test particle, say an asteroid, interacting with the Sun and Jupiter. In this case, however, it is placed near, but not exactly at, a 2-to-1 Jovian resonance. Once again, the solid thin lines are the prediction of the resonant plus secular theory solutions, and the dark lines, or points in this case, are the results of direct numerical integration. And again, we see that we have shockingly good predictive power, considering the vast number of simplifications and assumptions that have been made here. Remember, the secular theory predicted that we have no variation in semi-major axis, and the resonant theory predicted that we have sinusoidal variation in semi-major axis. However, we've derived this under the assumption that the variation in semi-major axis was very small. Both of these turn out to be the case. We do see variation in semi-major axis along with other periodicities and noise that has to do with higher order resonances and things that are not being considered. And then we see that this variation is quite small. This is all scaled by 10 to the 6th. We predicted sinusoidal variations from both secular and resonant theories in eccentricity, and we see that along with an overall linear drift, which is also very well captured by our theory. We do see a slight phase offset that causes these things to shift in time, so of course the theory is not perfect, but we never expected it to be. secular plus resonant perturbations in the longitude of periapsis predicted a linear plus sinusoidal variation, which again is exactly what we see. We can again see a slight phase shift due to a mismatch in periodicities, same as we had for the eccentricity. And we see that the linear slope is not quite accurate. Again, this has to do with all of the various effects that are being captured by the numerical integration that aren't included in our model. And finally, we predicted only a linear variation in the longitude of the ascending node from the secular theory and no variation from the resonant theory. And again, we see primarily a linear shift in capital omega, but again, with higher order effects that we are not capturing with our model. As a final note on this, consider this denominator term 2n3 minus n2 minus varpi dot 2. This same exact denominator term is going to arise in both the expressions for a2 dot and varpi 2 dot for the resonant theory. So what that means is that as we approach exact resonance, as this combination goes to 0, we will have growth in the amplitude of all these variations, meaning a growth in the variation of varpi 2, and thus growth everywhere. And so what this actually is telling us is that this simplified model is going to start breaking down as we approach exact resonance. We will need to do a little bit more work to get an analytical expression that is good for matching exact resonances. And this theory is really only good for approximate resonances or near resonances, as we were treating in the example shown in the slide. Let's zoom out a bit and consider where we are at this point. We've now shown that we can get surprisingly good predictive power from our low-order linearization of the Lagrange planetary equations and low-order expansion of the disturbing function for secular perturbations and for resonant perturbations. But if we think about this a little bit further, this leaves open the question of just which resonances we should consider when we are treating an arbitrary system. We did analysis for a near resonance, and because resonances are just near integer ratios of periods, if we go to arbitrarily high integers in those ratios, we can always find a near resonance to any pair of orbits, even a pair of orbits that has a completely irrational ratio of orbital periods, like the case where you have a pi/1 orbital period ratio, can be approximated to some finite order by a pair of ratios. We know that pi can be approximated by 22/7 or any higher order approximations. So does that mean that that pair of orbits is actually near a resonance and we have to consider those resonant terms? To find out, let's go back to our basic statement of the disturbing function. From our study of the Legendre polynomial expansion of the disturbing function, we know that the disturbing function on body 2 can be written as the gravitational parameter of body 3, the external perturber, times a summation of some s values, which are functions of the semi-major axes and eccentricities and inclinations of the two bodies, times the cosine of our generalized argument phi. Furthermore, from our second order expansion of the disturbing function, we know that we can write this generalized argument, which we will call was composed of integer values multiplying lambda 3, lambda 2, varpi 3, varpi 2, and omega 3, omega 2, instead as linear combinations of other sets of integers, L2, M2, P2, P3, Q2, and Q3. And you will have to excuse the notational overload here. M2 is a scaling integer, not the mass of body 2, but we have once again quite literally run out of letters. So what we are positing here is that we can write our generalized cosine argument phi as L2 minus 2P3 plus Q3 times the lambda 3 term minus L2 minus 2P2 plus Q2 times the lambda 2 term, and so on and so forth. You can verify that this is true by inspecting our existing expansion of the direct and indirect parts. That is, you can literally try to match that form of the generalized argument to all of the various cosine arguments that you see here, here, and in this slide as well. And you will find that it works. If you sum up all of these coefficients, C1 through C6, you'll notice an interesting thing happens. Every single thing in here cancels. We have one instance of positive M2 and one instance of negative M2. We have two instances of positive L2 here, and two instances of negative L2 here, and so on and so forth. When you sum up these 6 coefficients, their sum will be 0. And this is known as the D'Alembert relation. And it's important to pause here and state that the D'Alembert relationship is specifically tied to this choice of angles. It is not going to work for any arbitrary form of the generalized argument here, but to the specific one that has been developed. In particular, it is important that all of these angles be with respect to fixed directions. And that is why we have developed all of this formalism in terms of longitudes rather than in terms of anomalies. If we return to this summation, we still have to consider this S term. This S acts as the amplitude of these cosine terms, and so can be thought of as the relative strength of each of those terms. This S can also be expressed in terms of the various quantities that we've previously established, including this four-dimensional A matrix and these epsilons and everything else that you see here. From that earlier development, we can show that S can be approximated by some function of the Laplace coefficients with arguments of delta, our semi-major axis ratio, scaled by A3 times the eccentricity of body 2 to the absolute value of this Q2 integer times the eccentricity of body 3 to the absolute value of the Q3 integer times S2, which recall was sine of half the inclination of body 2 to the absolute value of this argument. This is the argument that is multiplying omega 2. And finally, times sine of 1/2 of the inclination of body 3 to the absolute value of the argument that is multiplying capital omega 3. So how does this help? What we've shown here is that the strength of the cosine terms in our infinite expansion is going to go as the eccentricity of body 2 to the absolute value of Q2. Since all of this analysis is only really good for closed orbits, and especially those with low eccentricity, because we expanded around 0 values of eccentricity and inclination, what this says is that as Q2 increases in either direction, positive or negative, the strength of the term decreases. The same is true for the inclination terms with these specific combinations of arguments. Now, these coefficients, you'll recall, are also the things that give rise to the resonant perturbation relationships. C1 and C2 here are what we dialed in to get our approximate 2-to-1 resonances. As the integer values in these ratios grow, so too will these coefficients. And that means that the higher the order of the resonance, the larger the integer values involved in that resonance, the smaller the power of the perturbation. And this is the basic fact that allows us to only consider a finite set of resonances, really only the lowest order ones, and not worry about harmonics and aliases and very, very, very high order approximate resonances, because their strength in a perturbative sense in this low order expansion will be very small compared to that of the low order resonances. And that is really why this analysis works. Because even though it is possible to find an integer ratio that is near resonant for any arbitrary pair of orbits, it is only the orbits that are actually near low integer ratio resonances that will see those resonant perturbations to any great degree.